Thank you very much. So this is my, thank you, first of all, thank you to the organizers for the invitation to give this talk. This is my first Zoom talk, so we'll see how it goes. If I'm somehow, if a question is posed on the chat and I miss it, please interrupt me or just interrupt me in any way. So yeah, so this is going to be, well, first I should somewhat apologize. This is going to be essentially a talk about algebraic topology, even though this is a symplectic geometry seminar. But it's algebraic topology, which I believe is relevant for symplectic geometry. So yes, right, it will be about the Pontryagin-Thom construction for orbifold bordism. So specifically what I mean by that is, so you can define bordism groups based on orbifolds instead of manifolds. And what the Pontryagin-Thom theorem tells you is that, well, what it tells you for manifold bordism groups is that those bordism groups are certain stable homotopy groups. So the goal of the talk is to tell you how to generalize that to orbifolds. Okay, so to begin with, let's talk about some of the setting we're in, which is the setting of Orbispaces. So an Orbispace, by definition, is a space. Space is sort of in quotes here. It's something, it's some object which is locally isomorphic to the quotient of a topological space by the continuous action of a finite group. Now, to make this sort of thing precise, you need the language of stacks, and this is not a. This talk is not meant to be somehow an introduction to that language. If you already know it, great. If you don't, it won't really matter. The important part is an Orbispace is somehow something which is covered by some atlas by things which are of the form topological space modulo continuous action of a finite group. Okay, so what are some examples of these things? The example you're probably all familiar with is orbifolds.
John, there's a question.
Yes.
So separated, the Deuce asked, so separated, does it mean the analog of Hausdorff?
Yes, it is the analog of Hausdorff, and what it means is that the diagonal map is separated and proper. Yeah, maybe I can. Yes, yeah. So I can even so separated means this diagonal is separated and proper, and Étale atlas. Oh, this is for the stacking people. Great. So examples, orbifolds. We've probably all heard about orbifolds before. These are an example of an Orbispace. The moduli stack of Riemann surfaces of genus G is an orbifold, hence it's also an Orbispace. Moduli stacks of pseudo-holomorphic curves are also best regarded as Orbispaces. I mean, for many purposes, we just care about somehow the underlying topological space, but to do more complicated things with them, it's often useful to regard them as Orbispaces. Right? How do you get what would a local chart then be? Well, have some curve. Maybe it has some pseudo-holomorphic map. Maybe it has some automorphism group. So then locally, what does the moduli space look like? You can write down this standard Banach manifold picture, take the zero set of your Fredholm section, but then you have to quotient by that finite group, which is the automorphism group of the curve around which you're making the chart. So you get a chart exactly of this desired form, a topological space quotient by a finite group. Great. So finally, some very basic example of an Orbispace is just a point modulo the trivial action of some finite group gamma. So that's blackboard bold B gamma, which should not be confused with the topological space B gamma, which is Roman B, although when I say them, it's not really possible to distinguish, but written they're not the same. This and this are different. Okay, so let's keep going. Okay, so some important features of the Orbispace context, which are somehow new if you're just used to thinking in terms of about topological spaces. So the first, maybe the biggest one is that the space of the set of, there is no set of maps between a given pair of Orbispaces. There's no notion of equality for maps between Orbispaces. There's no notion of an isomorphism between maps of Orbispaces. If I give you two maps from X to Y, you can ask for an isomorphism between those two maps. You cannot ask for them to be equal, or at least you should not. You could ask for them to be isomorphic, but better you want to have an isomorphism between them. Every point of an Orbispace has a group attached to it called the isotropy group of that point. And if you view your point as somehow a map from the singleton topological space into your Orbispace X, then this isotropy group is literally just the automorphism group of that map. And these isotropy groups somehow, they're telling you the amount of orbiness in the space. So if all the isotropy groups are trivial, then you just have a space. An Orbispace is a space if and only if all the isotropy groups are trivial. And in terms of this local quotient picture, Y mod gamma, the isotropy group of a point is simply the stabilizer of that point under the action of gamma. Okay. Right, so isotropy groups are functorial. If you have a map, it reduces a map on isotropy groups. And here's an important definition. A map of Orbispaces is called representable if and only if these maps on isotropy groups are all injective. So if you're familiar with the language of stacks, you'll know that there's a general notion of a map of stacks being representable, and one can check, it's not entirely trivial, but one can check that a map between Orbispaces is representable in that sense, if and only if it's injective on isotropy groups. So for the purposes of this talk, we can just regard this as the definition if we want to. If you have a representable map, you can form the mapping cylinder. This is a familiar construction in algebraic topology, forming mapping cylinders. And in order to sort of do algebraic topology with Orbispaces, we certainly want to be able to do this. And we can do this provided the map is representable. Otherwise, in general, we cannot, at least if we want to stay in this world of stacks with an Étale atlas. A big warning, though, is that usually you cannot contract the closed subspace to a point. This is another thing we really like to do in algebraic topology. If you have some closed subspace, take the quotient space, where you just contract the space to a point. This usually doesn't make sense. At least the quotient in any reasonable sense would not be an Orbispace. So one has to be careful. It doesn't usually cause too many problems. You can get around this, but one should be careful. Yeah. So to answer Hiro's question, yes, these are this moduli stack. I guess I should say it to everybody. This moduli stack is I should say stable here. Or equivalently, G is at least 2. Great. Yeah, so one can just sort of go through Hatcher and say, what if this makes sense in the Orbispace context? Can we just do algebraic topology with Orbispaces? And for a lot of it, you can. So the most basic definition is, of course, CW complex. So what is that in the Orbi setting? So an Orbi CW complex just means we take a bunch of cells, which are a disk, cross B gamma. B gamma, remember, is this. B gamma is point longitudinal gamma. So these are the basic cells by which you can build up an Orbispace. Okay, Igor asks, what's the intuition behind injectivity in the definition of representable? So I don't know if this is intuition, but you can ask yourself, if I have something like a map from BG1 to BG2, and I want to pull it back along a point and say what goes here, then, well, what will go here is, well, at some number, it will be some number of copies of B of the kernel. So this is maybe B, and what goes here is a disjoint union of copies of B of the kernel of phi. So if you want this map to be representability means somehow any pullback is supposed to be, if this thing over here is a space, then the thing you get over here should also be a space. That's the definition in the stack theoretic sense of being representable. So you see, if I want this to be a space, the kernel better be trivial. I'm not sure how much intuition that is, but anyway, that's another. That's essentially a proof that is at least a proof that if you are representable in the stacky sense, then you're injective on isotropy groups, and the content, the tricky part is the converse. Okay, so going on. Okay, so an Orbi CW complex is built by attaching these cells. Key is along representable maps. You can only attach along representable maps. Okay, so here I've just written out the usual definition of the CW complex. You start with the empty set, and that's the -1 skeleton, and the K skeleton is obtained from the K-1 skeleton by attaching some number of disks. Here are, again, along these. These are the attaching maps, and they're assumed to be representable. So this notion of cellular Orbispace was introduced by Geffner and Enriquez. This is a slight modification of their definition, but it's essentially equivalent to it. Okay, so lots of algebraic topology just works verbatim for this. Cellular approximation, for instance, just goes through just fine. Here's something which requires a little bit more non-trivial. So what are the analog of homotopy groups in this setting? Well, so first, what's a base point? A base point is a map from this stack BG into X. We need this more general notion of base point to really have homotopy groups which capture the algebraic topology of our Orbispace X. So if you have such a base point, P a map from BG into X, you can define the homotopy groups. Sort of G homotopy groups, you might call these G fixed point or G equivariant homotopy groups. I'm not sure whichever one you want to call them. Just homotopy classes of maps from the sphere cross BG into X. And these should be based maps. Since the restriction to a base point cross BG inside the sphere cross BG is identified with P. So homotopy classes is this set, and as usual, when K is at least 2, this is a group. This is an abelian group. When K is 1, it's a group. When K equals 0, it's a pointed set. And if you forget the base point, it's a set which is independent of the base point. Okay, so for this notion of homotopy groups, you have Whitehead's theorem. A map of Orbi CW complexes is a homotopy equivalent if it induces isomorphisms on all of these homotopy groups with respect to all base points. Now, I want to say one remark about this all base points thing. It's common when you're just talking about spaces to want to sort of simplify your situation so that you can get rid of this all base points thing and just talk about one base point. So if you talk about connected pointed topological spaces or connected pointed CW complexes and pointed maps, then you can just use that single base point to define your homotopy groups, and you can say, well, if you induce isomorphisms on those homotopy groups with respect to that single base point, then you're an isomorphism. So that's, and it's sort of obviously, this is obviously equivalent to the usual statement of Whitehead just by working component by component. Now, you can't really make such a simplification here, because even if a space is connected in the sense that pi 0 with respect to the trivial group is a singleton set, it may be the case that pi 0 with respect to a non-trivial group is not the singleton set. I mean, so it might not be somehow G connected for every G. And there's no real way of getting around this by somehow splitting up into different connected components, because your space might be connected but not G connected. And so you really need all base points here. Okay. So finally, one last sort of general statement about the topology of Orbispaces. There's this result enough vector bundles. So this was conjectured by Andre Enriquez. And so as the statement, so first of all, let me say, if you have a vector bundle over an Orbispace, what are its fibers? Well, if you take a point X with automorphism group G sub X, the fiber E sub X of the vector bundle over that point carries an action of the isotropy group. So the fibers of a vector bundle are representations of the isotropy groups of the points of your Orbispace. And so you have sort of all of representation theory potentially appearing when you study vector bundles over Orbispaces. In particular, in usual algebraic topology, when studying vector bundles, it's sort of a fact which is used all the time, almost without thinking about it sometimes, is every vector bundle, say over a compact space, every vector bundle embeds into a trivial vector bundle. So this is no longer true in the Orbispace context, because once you have some isotropy group representation which is non-trivial, you're never going to be able to embed that into a trivial vector bundle, because that would entail embedding a non-trivial representation into a trivial representation when you specialize to a given fiber. So this result about enough vector bundles, it somehow allows you to make these arguments, which in usual algebraic topology would rely on the fact that somehow embedding something into a trivial vector bundle. Okay, so what does it say? It just says, well, for simplicity, we could say maybe X is compact Orbi CW complex. There exists a finite dimensional vector bundle over it, such that the isotropy group representations have all of their isotopic pieces are non-trivial, or equivalently, they're faithful representations of all of the isotropy groups. Okay, so this will be useful at various later points. Okay, so now let me introduce orbifold bordism, because this is the main player for one of the main players in the Pontryagin-Thom isomorphism. Okay, so orbifold bordism is going to be a homology theory for Orbispaces. And right, what do we know about from Eilenberg? What do Eilenberg's tell us about homology theories? They're functors on pairs. So let's begin with an Orbispace, an Orbi CW pair. So just an Orbi CW complex and the subcomplex. And so then we can define this bordism group, directly generalizing what we would say for just the bordism group of an ordinary CW pair, which is that we just take compact orbifolds with boundary and a map from M to X, which sends the boundary of M into A. And these are considered modulo bordism. And I'm going to impose the requirement that these maps are representable. So in particular, if X comma A is an ordinary CW pair, that is, if when you glued it up out of cells, you always took gamma to be trivial, then this is just usual bordism classes of manifolds, because if you have something with a representable map to a space, well, that thing, the domain, better have trivial isotropy, because representable means injective on isotropic groups. So, so this is when you take this definition, you restrict it to ordinary CW complexes, you get bordism in the usual sense. So in that sense, it's a very natural generalization of bordism to the Orbispace context. And the other comment about this requirement about things being representable is that even if you decide you care about all maps or orbifolds into your Orbispace, you say you don't want this restriction to representability. The groups you get can be described in terms of the groups I've written down here, because of this adjointness property. So I guess I didn't really write down the definitions of these categories. I will later. The object of these categories are ORBCW complexes. The morphisms are different. So on the left, we take only representable morphisms. On the right, we take all morphisms. And one can check this functor has a right adjoint. And what that means concretely is for every Orbispace, say every ORBCW complex, call it X, there's an ORBCW complex called R of X, such that maps to X is the same thing as representable maps to R of X. So if you cared about bordism of all maps to X, that's the same thing as bordism of orbifolds of the representable maps to R of X. So for example, just bordism of orbifolds with no extra structure, just bordism of orbifolds is the same thing, of course, as bordism of orbifolds with a map to a point. So that's, and a map to a point is the same thing as a representable map to R of a point. So this group of bordism classes of closed orbifolds, it's this orbifold bordism group I've written down of R of a point. R of a point is some sort of mysterious space, which mysterious Orbispace. It has various concrete descriptions, and it will appear later as well. Isn't the group 0 if representability is dropped? I don't believe so. I mean, for example, as a point is the boundary. I mean, it's definitely, I mean, bordism classes of closed orbifolds. I mean, if you decide you want to say, yeah, I mean, if for example, you used oriented orbifolds, it's definitely non-zero. Okay, so there are various properties of this orbifold bordism. First, it satisfies excision.
There is a question from Thomas Roth.
Yes, no, I said something about this. I don't think it's.
Sorry about it.
Okay, so it satisfies excision. This is essentially obvious. The same proof as for usual manifold bordism. Exactness is also obvious. Well, the same proof is the proof is the same as for manifold bordism. There are so-called inverse Thom maps. This is Shveda's terminology. So if you have an Orbispace X and a vector bundle over it, well, first of all, you can form the Thom space. That's this thing over here. This is the Thom space of V, the relative Thom space. And if you have an orbifold mapping to X, then you can pull your vector bundle V back to that orbifold and take its Thom space. And Thom space is functorial, so you get an orbifold mapping to the Thom space of V. And that's exactly what this map is. Passing from an orbifold to the Thom space of the pullback of V. So this is called the inverse Thom map. It exists for any vector bundle. Remember, vector bundles over Orbispaces are very, even vector bundles over B gamma, right? Maybe I should say this over. So vector bundles over B gamma is just the same thing as representations of the group gamma. So a vector bundle is called coarse if all of the isotropy group representations are trivial. So equivalently, it's pulled back from the coarse space of your Orbispace. So for those vector bundles, this inverse Thom map is an isomorphism. And what is the inverse to it? If I have an orbifold mapping to x to the v, what I can do is I can intersect with the zero section, and I get something mapping to x, and at least formally its dimension goes down now by the rank of v. There's of course a little bit of a hiccup though, because I never said anything about this intersection being transverse, and if I want to get an orbifold out at the end, I better argue that this sort of arbitrary orbifold mapping to the Thom space of x, Thom space of v over x, I can be perturbed so as to be transverse to the zero section. So when I intersect, I can actually get this is sort of intersect with zero section of v. And the point of v being coarse is that that's the hypothesis you need to do this perturbation, to make the intersection with the zero set of v transverse and actually get an orbifold out. Okay, and once you check that this map actually makes sense, it's sort of easy to check that it's an inverse to the inverse Thom map. But when v is not coarse, the inverse Thom map is generally not isomorphism. Okay, so now let's go on to derived orbifold bordism. So I just now hit on this fact that equivariant transversality is often just false, and because of that, there are two natural flavors of bordism in the Orbi context: orbifold bordism, as I just defined it, and derived orbifold bordism. So let's define derived orbifold bordism. So the first definition here is a derived orbifold chart is just a triple D, E, S. So D is an orbifold, E is a vector bundle over D, and S is a section. And we think about this as a presentation of the zero set of S. So for example, if I decide I want to just throw away parts of D over which S is non-zero, that doesn't matter. It's somehow, for all intents and purposes, the same object after doing that. So that's this first operation here, restriction. That just means replacing D with an open subset which contains the zero set of S. There's another slightly more complicated natural operation called stabilization, where you take, you increase the dimension of your parameter space by replacing D with the total space of a vector bundle F over it. So if I did just that, that would have the effect of replacing S inverse of 0 with the total space of F over S inverse of 0. But I don't want to do that. I want this operation to preserve the zero set. So the natural thing to do is to also add F to the obstruction space E. And then S, the component of S mapping to F is now just the identity section. So somehow you add F to both the base degrees of freedom in D and to the fiber requirements in the obstruction section. And And so in the end, the zero set of S is unchanged. Okay, so both of these operations should be regarded as leaving the underlying somehow intrinsic derived orbifold unchanged. Okay, and finally, we don't care that D be compact. All we care about is the zero set of S to be compact. So compact should just mean the zero set of S is compact. So here's a definition, except it's not definition. A derived orbifold is some sort of object with an open cover by derived orbifold charts, modulo restriction and stabilization. So there are various ways of making this precise. Spivak wrote about derived smooth manifolds. Joyce has written a lot about D orbifolds, derived orbifolds, and various others as well. Maybe so many that I shouldn't try to list all of them, but for the purposes of this talk, we're not going to use this notion. So the corollary of enough vector bundles is that every compact derived orbifold has a global chart. And this is great because it means that to define these derived orbifold bordism groups, we don't have to grapple with this definition of what it means to glue together these derived orbifold charts. We can just use charts, use global charts to define these bordism groups. There is, however, a cost to this approach, which we'll see very soon, but we can deal with it. Okay, so we can now define the derived bordism group of a space, of an Orbispace pair X, comma A, is defined in the same ways manifold of underived orbifold bordism groups. You just look at compact derived orbifold charts, a map to X, and we have the same relations as before, bordism, and then we add restriction and stabilization as well.
So, John, I have a very naive question. So why is this called derived?
Derived. Yeah, so I think one origin is that these objects should be viewed as arising for one way these objects arise as by taking a fiber product. If you have some fiber product, if you have some manifolds here and this fiber product is not transverse, then you don't get then this is not a manifold. But in some sense, the derived fiber product should be a derived orbifold.
Thank you.
There's probably a better answer, which I'm not thinking of right now. Okay, so one thing you might notice about this definition of derived orbifold bordism is that it's not obvious that this is an equivalence relation. So not obviously equivalence relation. So, I mean, it turns out you can form an equivalence relation with this if two things. So first you have to, so if you have two derived orbifold charts mapping to X, if you first restrict, then stabilize, and then ask for bordism, that's an equivalence relation. But it's a non-trivial to check this, and the content is precisely enough vector bundles. This would obviously be an equivalence relation if we define this bordism group in terms of derived orbifolds, because somehow then you just glue them together, as you do for bordisms of ordinary orbifolds. Okay, so that's one of the subtleties in the definition. You have excision. That's again obvious. Exactness is not obvious. It now requires an appeal to enough vector bundles. So that this is the cost of defining derived orbifold bordism in terms of charts rather than in terms of honest derived orbifolds. It means that enough vector bundles is somehow gets caught up in, it becomes required in proving somehow any non-trivial properties of this derived orbifold bordism groups. Okay, so now we have inverse Thom maps for the derived orbifold bordism groups. They're defined the same way as before, just past the Thom space. But now these are always isomorphisms. And the reason is simply that, I mean, I gave you just a few minutes ago the recipe for what's the inverse to the inverse Thom map. And what is it? It's just intersection with the zero section. And we had to have some non-trivial discussion about when is that transverse. But in the derived context, we don't care. We're just allowed to add V to the obstruction space and add the identity to S. And that gives us a map in the reverse direction, and you check it's the inverse. Okay, so in the context of global homotopy theory, Stefan Schwede has shown that in the homotopical sense for corresponding homotopical bordism theories, derived version is a localization of the underived version of the inverse Thom maps. And the same thing is true in this context as well. Okay, so let's see. Hirobi Tanaka has a question. So D is definitely an orbifold, and we're definitely not going to. I hope I'm answering your question. I'm not exactly sure what you're asking.
Right, I was just asking what you meant by a global chart. For example, like for just Dilley-Mumford stacks, you could also have a notion of a global chart. It's just a presentation.
Yeah. So global. I just mean that there's a single derived orbifold chart which describes the whole derived orbifold, rather than somehow having to glue a bunch of them together.
Okay. Thank you.
So in the case of an ordinary orbifold, it's already somehow a global chart. We don't need to somehow. Yeah, I'm not talking about saying a global quotient. There's no global gamma. There's no global group. That does not get globalized. Definitely. Just some of the obstruction space which gets globalized. Okay. So the next thing I think I should say is, so whenever we're talking about bordism groups, we can talk about bordism with tangential structures. That just means I add some extra structure to the tangent bundle. So I consider bordism of manifolds with an orientation or with a stable almost complex structure or with a stable framing. That's all structure that you impose on the tangent bundle. So there's a remarkable result of Wasserman, which implies that you can view orbifold bordism as derived orbifold bordism with tangential structure. And this is pretty important in this story because it's what allows you to extend orbifold bordism from the category of Orbispaces to the category of Orbispectra. Okay, so first of all, as I've said before, so someone is requesting remote control of my screen. I think I will decline this. I assume you just pressed the wrong button. Okay, so now I have to get my scrolling back. Scrolling. Okay, so for finite dimensional real representation of a finite group, we have decomposition into canonical direct sum decomposition into pieces indexed by the irreducible representations of your group. And so that's G hat is the set of irreducible representations. And in particular, I'm interested in this subspace where we take all the non-trivial irreducible representation. So just throw away the component on where G acts trivially and keep everything else. So if you have a vector bundle over an Orbispace, you can do the same thing with respect to the isotropy groups. So look at a given point X, you look at the action of the isotropy group that acts trivially on some piece, and you just throw that away. So this is not a subbundle, but it's somehow a vector space associated to each point. Subspace V associated to each point. So here's Wassermann's theorem. So it's, we know, right, if you have a vector bundle over an orbifold, there definitely need not be a section which is transverse to 0. But Wassermann gives a sufficient condition for this to be the case. Now I'm crediting this result to Wassermann, even though he only proved a very, very special case of it. So what does the result say? So if you have a map from the tangent bundle of X to E, for which its restriction to this funny looking subbundle iso hat -1 is surjective, then you can have a section which is transverse to 0. And the corollary you get is that ordinary bordism can be described in terms of bordism with derived orbifolds as follows. So you take derived orbifolds, again representable over X. And so this thing on the left here, you should consider to be the tangent space to the derived orbifold. So maybe I'd just call this the tangent space to D, E, S, is that. And what you're saying is that I want this virtual vector bundle to be of the form some vector bundle minus a trivial bundle. And if I impose that sort of extra tangential structure, what I get is ordinary bordism. So I've described here ordinary bordism purely in terms of derived objects. And yeah, so this is crucial, as I said earlier, this is crucial for extending orbifold bordism from Orbispaces to Orbispectra, which will be necessary for the Pontryagin-Thom isomorphism. Okay, great. So so I just gave examples of homology theories for Orbispaces. Now let's talk about some cohomology theories for Orbispaces, because this is what's going to be on the other side of the Pontryagin-Thom isomorphism. So there's a field of global homotopy theory, which is essentially it is a way of doing algebraic topology with Orbispaces, although it's not somehow necessarily phrased in that way. It's somehow an equivalent theory, or at least partially equivalent. So in particular, I'm just going to take a very small part of this theory of global homotopy theory, the global spectra. So that's the analog of spectra in global homotopy theory. And what they do is they give you cohomology theories for Orbispaces. That's one thing they do, at least. Okay, so we have this category of orthogonal spectra. That's a functor from the category of real inner product spaces to spaces, and to an inclusion of one orthogonal space into another, you associate a map of spaces. Okay, and there's a definition, there's a notion of when a map of orthogonal spaces is a global equivalence. I will not give that definition, but the localization of orthogonal spectra to global equivalences is this category of global spectra. And there's a model category structure on orthogonal spectra called the global model structure, in which global equivalences are the weak equivalences. And so you do have an effective way of understanding this localization. Okay, so these are some examples of orthogonal spectra. The latter two are defined by Schweda. First one is simply the sphere spectrum. Okay, so here's the definition I really want to talk about. So this says this is the recipe for going from a global spectrum to a cohomology theory for Orbispaces. So if I have an Orbispace and the vector bundle over it, what I can do is I'm talking about this here. What I can do is I can apply Z fiberwise. Z is an orthogonal spectrum. I can apply Z fiberwise. So, right, Z takes a vector space to a space, and it somehow does so continuously. It's a continuous vector. These are topological categories. And so it makes sense to apply it in families. Right, like if I have a vector bundle, I can take the fiberwise one point compactification of it and get a sphere bundle. And that would be the same thing as applying this orthogonal spectrum here to that vector. And you can do the same thing with any orthogonal spectrum. So I get this fibration, and you can look at sections. And homotopy classes of sections is by definition this value of the cohomology, the Z cohomology of X. Now you have to take a direct limit over all vector bundles over X. Okay, so you can see pretty easily it satisfies excision and exactness, and so it deserves to be called the cohomology theory. And again, I'm approaching this via, in the vector bundles, this you might guess, and you would be correct, this definition is not going to be of much use if you're on if X does not have enough vector bundles. There are other ways of making this definition which don't require enough vector bundles, but I'm going to use this one. Okay, so now I think we can finally get to the Pontryagin-Thom isomorphism. So let's recall what it says for ordinary topological spaces. So you have a topological space X. Bordism classes of manifolds mapping to X is the same thing as stable homotopy classes of maps from the sphere spectrum into X smash MO, where MO is this Thom spectrum MO. Oh, this gamma means sections. And this means supported away from A. So Z of E is a fibration over X. This, and we're just taking sections of that.
Oh, I see. So this gamma, this pi naught gamma, that whole thing is sort of separate from your parentheses. This parentheses is just explaining what Z of E is.
Yeah. Oh, yes. Sorry. Yes. This is an aside. This is an aside here. That's
yeah. I was totally confused. Yeah, okay, thank you.
Yeah. Okay. So yeah. So this is this Pontryagin-Thom isomorphism, and there's also the version for framed bordism. If you have bordism of manifolds with a stable framing of the tangent bundle, that's just the stable homotopy classes of maps from the sphere to X. And everything in between works for any number of versions with tangential structure, almost complex bordism, etc. But let me just stick to these two. Okay, so this is not exactly the form that Pontryagin-Thom isomorphism will take for Orbispaces. We need to transfer it into a different form. So for that, we need to use Spanier Whitehead duality. So there's a category of finite spectra. These are just a formal desuspension of a finite CW pair. Those are the objects. So those are the finite spectra. Okay, so this category has a contravariant involution called Spanier Whitehead duality. One rather opaque way of defining it is it satisfies this universal property. So it's making it the so-called monoidal dual with respect to smash product. A more concrete way of defining it is the following. So take a manifold pair, what I'll call a manifold pair X comma A. So that means X is a compact manifold with boundary, and A is a codimension 0 submanifold with a boundary. So X comma A is some pair. Its Spanier Whitehead dual is given by this formula on the right here. I again take X. I now make it relative to the other part of the boundary, complement of A, and I desuspend by the tangential. Okay, so that's a more concrete definition. So using this duality, while using the universal property, we can restate Pontryagin-Thom as this isomorphism here. So we just put X to the other side using the dual. So this is the form that Pontryagin-Thom isomorphism takes in the Orbispace context. So here's a theorem for any finite Orbispectrum X. We have these natural isomorphisms. There are two distinct forms of the spectrum, and there are two natural ways to generalize the spectrum MO to a global spectrum. Those are these little MO and capital MO that are defined by Schweda, and they correspond to bordism and derived bordism. If you use the sphere spectrum, you get framed bordism. So I didn't define framed bordism, but if someone wants to ask after the talk, I can if you like. Okay, so I haven't yet defined Orbispectra or the involution D, but that's what I'll do in the rest of the talk. And then we will have a complete statement of the Pontryagin-Thom isomorphism. As with the case of the usual Pontryagin-Thom isomorphism, once you formulate it, the proof is not all that difficult. It's somehow finding the correct statement, and then that's more non-trivial. Okay, so let's talk about categories of Orbispaces and Orbispectra. So first, just various categories of Orbispaces. So spaces, CW complexes, continuous maps. There are two ways to generalize this to Orbispaces. You can take Orbi-CW complexes and all maps, or just restrict to representable maps. And I think it seems to be due to Gepner and Enriquez that you can do homotopy theory in either of these settings, and both are reasonable ways of doing homotopy theory. So you really get honestly two different ways of doing homotopy theory with Orbispaces, and it's not really clear which of these categories really deserves the name homotopy theory of Orbispaces. Okay, so there's these obvious functors from relating these categories, and they have various adjoints, which I think for reasons of time I won't say more about right now. In order to do spectra, we need to first go to pointed spaces, pointed CW complexes, and pointed maps. This is a familiar category. Now, I mentioned at the very beginning, if you have an Orbi-CW pair, it's usually not possible to quotient by the second element of that pair. If you have a pair X comma A, you can't just form X modulo A and say, well, I have an ORBCW, that's an ORBCW complex. Usually that doesn't make sense. So, so the objects, so the notation on the left is meant to somehow tell you that this is the natural generalization to the Orbispace context of the category of pointed spaces. But it's not the category of pointed Orbispaces. It's the objects here are ORBCW pairs and some non-trivial notion of maps between them. And again, there are two ways of doing this, either all maps or just representable maps. Okay, so you can now formulate, so this is all just an aside, which maybe I'll skip for the time being. So now you can form the category of finite spectra. So that just means you take this category of finite ORBCW, finite CW pairs and take direct limit under applying the suspension functor. So concretely, an object of this category of finite spectra is a formal symbol sigma minus k of x, such as a formal desuspension of a finite pointed CW complex. And the morphism space is given by this direct limit over stabilizing, over suspending. So you can do the same thing in the Orbispace context if you like. You can consider this direct limit of iteratively applying suspension, this category of ORBCW pairs. But this is not the category we're interested in, because in this category, you can only desuspend by coarse vector bundles. You cannot desuspend by all vector bundles. So I mean, this is a very, very familiar thing in equivariant homotopy theory. When you form equivariant spectra, you don't want to stabilize just with respect to trivial G representations. You want to stabilize with respect to all G representations. Let's see. Right, question. When I write this, are there? So so you're asking about this notation here. So this just means exactly, well, modulo not having defined the dual yet. This just means the cohomology in the sense that I defined above. You take a vector bundle over dx and you look at sections. So there are lots of vector bundles over X. In particular, at points, they have all sorts of non-trivial representations. So these, they definitely enter. You definitely have lots of non-trivial representations going into the definition of this in the form of sort of all vector bundles over dx. Now, there's somehow no global group G going on here, so I can't really say all G representations. It's somehow the analog of that is saying all vector bundles. I hope that helps. Okay. Right. So this this category here. In this category here, you're allowed to desuspend by a vector bundle all of whose isotropy representations are trivial, because those are the ones which embed into trivial vector bundles. So we don't want that. We want something where we can desuspend by anything. So instead, I'm going to make this definition. So the space R of a point, this Orbispace R of a point, it has the property, the universal property, that the space of representable maps from any Orbispace into it is contractible. So everything, all the objects in this category of representable Orbispaces can be viewed as somehow lying over R of a point canonically. And in particular, if I have a vector bundle over R of a point, I can suspend by it. I can pull back and suspend. The vector bundle over R of a point gives me an endofunctor of this category, namely pull back and suspend. So I can take the direct limit, and that's this category of representable finite Orbispectra. So there's, if you want to define sort of orbispectra without this representable prefix, you have to do something else. But we only need the representable version now. So let me say this. Okay, I think I'm going to have to skip this, even though this is very interesting. So here's a theorem. Okay, there's a contravariant involution of this category of representable orbispectra, and it's defined by the same formula as Spanner Whitehead duality for usual finite spectra. The first remark about this is that it relies crucially on enough vector bundles, and I don't know how to prove it without using enough vector bundles. I wouldn't be surprised. I mean, if I were forced to guess, I would guess that there is a proof which doesn't rely on enough vector bundles, but it would have to be much more abstract than the proof I give. And another, perhaps maybe more interesting question is to find the universal property characterization of this duality. I mean, it's a really nice thing to have. It's a category with an involution. I mean, it has to satisfy some nice universal property, but I don't know one that it does. It does not satisfy the same universal property. It does not satisfy the same universal property as Spanner Whitehead duality. It's not the monoidal dual with respect to smash product. It's not, and the reason is that somehow representability does not play well with product. If I have a representable map to X cross Y, that's not really easily relatable to representable maps to X and representable maps to Y. Okay, so questions. My orbi pairs is A always a subset of the boundary of X? Right, so there are two concepts. So an orbifold pair, yes, an orbifold pair is this, yeah, so this means, yes, that A is a subset of the boundary of X. This is codimension 0, and X is compact orbifold with boundary. This is in contrast to an Orbi CW pair, which can be anything. Okay, what is the motivation? What is the motivation for not relying on enough vector bundles? Right. So there are possibly many, but one good answer to this, I think, is that enough vector bundles is simply false in the more general context of Lie Orbi spaces. So if you want to allow sort of just Orbi CW complexes, which you get by gluing together, sort of allowing BG, where G is a compact Lie group. In this more general context, enough vector bundles just fails. It's just wrong. And so this is definitely a context you'd like to talk about. Okay, I'm already a little bit over time, but let me just say a few more things.
It's okay, John. You can take more time. It's fine.
Okay. It's over Zoom, so people don't have.
No, but also we have time till I mean, for discussion and questions till 45 past, so you can take more.
Okay. So since maybe this is the end of the official time, I'll keep talking, but people should feel sort of more free to interrupt questions. Okay, so given this D, we can define the homology of any Orbi spectrum by just saying we take the dual and then take cohomology. And it's a little bit strange. The cohomology, the E-cohomology functor that I defined above, is functorial under all maps, but this E-homology functor is functorial only under representable maps, because this contravariant involution D, this representability here is really important. If you try to do the other category where it's finite Orbi spectra, I don't think it has an involution like this. It shouldn't. So another way of saying almost the same thing is that sort of in usual stable homotopy theory, we have this isomorphism. I mean, maps from the dual of X to E is the same thing as maps from the sphere spectrum to X smash E. And this right-hand side is what's usually taken, it's usually told as this is the definition of, you know, the the E-homology of X in stable homotopy theory. But at least for finite spectra, the left-hand side works just as well. You could take that as the definition. But the funny thing is that in the Orbispace context, this is no longer an equality. It's just not true. And so, you have two things which you could reasonably call the E-homology of X. And somehow the only reason I chose to write this definition right here using the left-hand side instead of the right-hand side is that this is the one, the left-hand side is the one that's relevant for the Pontryagin-Thom isomorphism. Okay, so one last thing to say is that essentially the same discussion, the same proof of Pontryagin-Thom gives you a description of the morphism spaces in these categories of spectra in terms of bordism groups. So if I have Orbi CW pairs X comma A and Y comma B, each carrying a vector bundle, then I can look at the space of morphisms, right, from the dual of the first one to the second one. And there are two categories here I might consider: the Orbispaces, Orbispectra, or representable Orbispectra. And in each case, there's a description in terms of bordism of something, bordism of derived orbifolds with some extra structures, some maps to X and Y, and a marking of the tangent bundle. Now, you can see here, so this is why I said that this category should not have an involution. So if we're looking at this category, and both these maps are required to be representable, F and G are required to be representable, then this data here is sort of obviously symmetric in X and Y. I can just swap F for G, and so I could even just define a category whose objects are triples X, A, C, and well, okay, maybe I couldn't literally do that, but anyway, you can see how the involution D acts on morphisms, just because it just literally exchanges F and G here. But if you're in this category of orbispectra without the representability requirement, one of these is representable, the other is not. So there's no reason, at least from this point of view, you wouldn't expect there to be an involution on this category here. Now, of course, it's very natural now to ask what happens if I allow both F and G to be arbitrary. So now I do get a category with an involution, but I just have no idea what it is. Yeah, okay, so I think this is a natural place to ask for more questions. I can, I'm happy to talk about some of this other stuff on the slide that I skipped, but maybe I'll pause for questions before doing that.
So let's first thank you. Top. Of course, now we're open for questions.
Feel free to just unmute yourself and ask.
Yeah. Maybe I just start with one that's very, right. So I had the same question as Dusa. Basically, how do you see applications of,
Yeah, so I mean, well, I can give a sort of answer to this, which is just to say that my original motivation for thinking about this is that, well, to find a somehow stable homotopy theoretic receptacle for the virtual fundamental cycle of a multi-space of pseudo-holomorphic curves, which somehow would capture the entire derived manifold structure. And right, these geometrically defined bordism groups are nice, but somehow if one is going to do stable homotopy theory, it's often nice to also sort of have this isomorphism with somehow an object on the stable homotopy theoretic world. And I could certainly imagine that for doing Floer homotopy theory in a way which captures the structure of the moduli space of pseudo-holomorphic curves as a derived manifold, derived orbifold, and sort of remembers all of that data, that one would want to do something with global homotopy theory and view the your virtual fundamental cycles as elements on these right-hand sides, and in fact probably over here because you know you'll have an identification of what the tangent bundle is.
So is it correct to say that using this sort of stable or global homotopy theory and this Orbispace context eliminate some of the transversality or regularity issues that we generally encounter? Or so what do you need to be able to apply this for the type of moduli space of holomorphic curves?
I don't think it really changes what you need to do in terms of virtual perturbation, Kuranishi structures, that sort of thing. I think it somehow just tells you what is it that you want out of that. So the usual, I mean, to do say seventh Fukaya category or whatever, or Gromov-Witten invariance, all you need is somehow the fundamental class valued in like rational homology. But for these Floer homotopy theory arguments or other related things, you want a little bit more, and maybe the fundamental class in framed bordism. And when you have isotropy, there's no longer some classically known stable homotopy group which tells you the thing you should be getting, describes the group you should be looking for an element of.
Great, thanks.
So can I prove the same thing for MU or MU? So I certainly believe so. I have not, I was a little bit too lazy to try to write it down. Some of the problem is that there's these definitions of, so Schrader defines these other global spectra, MU and MU, which correspond to derived and ordinary stable almost complex bordism. One way you might try to define these spectra is by taking these definitions here, and saying, well, I want to replace this Grossmannian with the Grossmannian of not real subspaces, but real subspaces equipped with a complex structure, or real subspaces equipped with a stable almost complex structure, or maybe I really want to put a stable almost complex structure on the complement, or something like that. And that would somehow be the most natural way of defining it so that you can prove the Pontryagin-Thom isomorphism. Now, Schrader does something slightly different, which is instead, he just somehow does everything in the complex world. So MU of V, I'm probably going to get this wrong, but it's something like, you just take the complex Grossmannian in, VC cross the direct sum VC. You just literally complexify everything. So I believe the same result works, but I didn't check it carefully. Basically because I would rather somehow give the right definition of MO and little mo and capital MO for any sort of structure on vector bundles, like spin or anything. and prove it there. But that was a little bit more involved than I wanted to go at the time.
So John, in the setting that you're interested in for moduli of curves, I mean, you know, earlier we talked about how in this global setting, there's not like a single group G that you can study things with respect to, but it does sound like for every, you know, combinatorial type of Riemann surface that you're considering, there is like a global G's, you know, related to automorphisms of the Riemann surface that you care about.
What do you mean? What? Well,
like
I'm not sure. I mean, like, what if we just talked about like no nodes at all? That's a unique topological type, and then we have maybe you want to say then the group is the mapping class group, but still that's then not, you know, that's not a finite group. So, I mean, I guess you're right. Locally, there is a group, but somehow, again, that's just, there's locally a group, but globally, there isn't. There's somehow no, it's not like globally a quotient in some natural way.
I mean, that's because I guess you're insisting on Dilley-Mumfordness, but, you know, I mean, nowadays, like even in, you know, your paper with Vivek and Shio, like, you know, at least in the case of strips or cylinders, you do need to grapple with more Artin-like structures. It sounds like the group you care about arises subgroups of like BG, where G is the big continuous thing.
Yes, yes. I think that, yeah, no, I think you're right. Yeah, no, there yes. That's right. I mean, it's possible that this somehow helps. And in fact, there's a result of Look and Oliver. So this enough vector bundles, this is proven by Luck and Oliver if x equals y modulo gamma. That's not a very good modulo, is it? But, whatever. For gamma, a discrete group. So possibly infinite discrete group. And I'm embarrassed to say I don't actually know how somehow the gap between their proof and my proof. I mean, somehow a lot of algebraic topology, a lot of equivariant algebraic topology somehow just works somehow. The only reason algebraic topologists were not somehow thinking of, there was no reason algebraic topologists weren't thinking in the Orbispace context. It's just somehow they didn't have motivating problems which required that generality. So, you know, if you're an algebraic topologist who's only ever seen Orbispaces which are global quotients, maybe this is the only sort of Orbispace you'd ever think of. And so in that terms, they basically prove this enough vector bundle statement, although under this sort of global assumption. And I don't actually know how far off that is from the general result. Anyway, I sort of forgot the question I was answering, but hopefully I answered it. You can ask again.
But so like this desire to set up, you know, a kind of bordism theory and a stable homotopy theory that's good for these, you know, this orbifold setting. I mean, is it somehow philosophically equivalent to understanding, you know, essentially like sheaf theory over the stack of these Riemann surfaces? Like, you know, all these moduli spaces in floor theory, they obviously, you know, live over a stack of some moduli stack of Riemann surfaces, you know, that have been concatenated together through these breaks that appear. And I feel like if you understood sheaf theory of how things lived over there, I mean, I'm obviously inspired by my work with Jacob, but it sounds like there, like then the equivariance is kind of built in. I just have no idea how much more difficult these Artin things are in what you're considering. Yeah,
well, so okay, maybe this is only tangentially related to what you're actually asking, but it's definitely the case that right, somehow the most natural place for the virtual fundamental cycle to live is in bordism, so as I've defined it, but bordism may be applied to, right, this sort of this Artin stack mg n cross x, and if you wanted to say push forward this class here, and this is as you said, this Artin stack, and of course you can push it forward under the stabilization map to Dulin-Mumford, but maybe you don't want to. Maybe there's more information here. I don't. Yeah, I don't know how to get a handle on these groups, but there certainly could be interesting. Okay, so a question about the Orbifold Fukai category. So I'm not actually familiar with what the Orbifold Fukai category means, so it's hard for me to answer this one.
Actually, I don't know how those Orbifold Fukai category was defined, but I just have no idea about how how a Fukai category can be simulated via orthogonal spectrum. That's my point.
Yeah. I mean, so this somehow, yeah. I mean, this is somehow most directly relevant to the setting when somehow your moduli spaces of holomorphic curves have isotropy. So that can occur in many settings. But anytime you have bubbling, basically, is going to likely have also isotropy.
So there is also a question from Tony Barry. Do you want to ask?
Yes, thanks, Octavian. John, I'm just wondering if there is an analog of what we see in topology where things like MO and M spin and split into simpler spectra, like Ardenberg-MacLean spectra, and in the case of M spin, KO related spectra. Do you see any of that sort of phenomena? Yeah,
I mean, that's definitely an interesting question. The only answer I might be able to give is something which I would have read from Schweda's book. So I think the real answer is just, you should look at what he wrote there. I think he might have written something there, but I wish I knew a better answer.
So do analogs of characteristic numbers arise?
Characteristic numbers. Yeah. Again, I wish I knew. There's something I can say about this. There's definitely a thing about which of these is easier to calculate, the little mo or big mo. I think the derived version with the capital letters is easier to calculate for some reason. So inverting all these, well, after you localize it might be expected that it's easier to calculate that way.
Also related to the earlier question about MU, I mean, there must be some formal group type object lurking in all of this, surely.
I would definitely hope so. I mean, and again, this might be more amenable to calculation in the derived one, and that's perhaps even more motivation for introducing the derived version.
Thanks very much. A very nice talk. Thank you.
So, John, Hiro has another question, but this is really related to the question you really asked us to ask.
The framing.
Yeah.
Yeah. Let's see. So, so what should I say? So I think it's yeah. So maybe I'll just go all the way to the bottom here. I need a new page. Let me get some more. So some more time. Maybe I'll get a black pen so it's easier to read. So if I write framed bordism of x comma a, and in fact I'm going to tell you what framed bordism of of this is. So, so this is bordism of derived orbifolds. Representable map X comma A, and a stable isomorphism TC should be equal to, okay, I should put this map F upper star C plus, I guess, R to the D, and D is the grading here. So this is D here. I hope I've gotten the sign correct. This is minus C, and this is C here, I think. So maybe I should say what stable isomorphism means. So that means TC plus V is honestly isomorphic to F upper star C plus RD plus V for some vector bundle V over C. So this is somehow the natural way to, well, if you have an orbifold and you know what its tangent bundle is, then this is somehow the natural place to put the virtual fundamental cycle, or the fundamental cycle here.
So Hiro, that's okay? Good? Yes. All right, so let's see. I think we have still a little bit more time for more questions if there are. We're getting, Hiro has one more. Well,
right, so let's see. Yeah, so the proof, so it's actually not, yeah, so what's the point of this proof? So the first way to approach it is sort of via obstruction theory. I have my vector bundle over the K skeleton, I want to extend it to the K+1 skeleton. And so there are obstructions to doing this called Chern classes. And in fact, the Chern class, there's a refinement of it to a class on the inertia stack. So if you have a vector, so imagine you have a vector bundle over Y cross BG. So yeah, so this maybe I should go to the end here. So if you have a vector bundle in open Orbispace, you have this. I'll talk about the Chern character. This is something in the cohomology of X with coefficients in Q. There's something which I sort of want to call it the Chern character, but I'll instead call it the inertial Chern character. It's in the cohomology of the inertia stack of X. This is X cross X with X. And for example, if you have a vector bundle over, say, Y cross BG, then V is, right, this direct sum over, canonically, this direct sum of isotypic pieces. And the inertial Chern character captures Chern characters of all these V rows, whereas the Chern character V itself just captures the Chern character of the vector bundle V over Y. so the point of it, so the proof of enough vector bundles just goes by showing that I'm going to define the vector bundle by saying it's going to have the trivial inertial term character. And when you do that, you see there are no obstructions, or rather the obstructions are all rational. And so if you have a vector bundle, after you replace it by its direct sum of n copies of itself, eventually you can extend over to the next thing.
All right. Thank you very much, John, again for this very interesting talk. And thank you again, actually, in a more and